Now that we've defined sets, we can start talking about some operations on sets. For example, we could write A union B, and this corresponds to the set of all x such that x is in A or x is in B. So it takes all the elements in A, all the elements in B, and throws them into one set. So if A equals 1, 2, 3, and B equals 1, 5, 7, then A union B is going to equal 1, 2, 3, 5, 7. Notice I did not repeat the 1. You do not repeat elements in a set. Sets never have repeated elements. Okay. We could also define A intersection B, and this is equal to the set of all x such that x is in A and x is in B. So again, if I define A and B to be A is 1, 2, 3 and B is 1, 5, 7, then A intersect B is simply equal to the singleton 1. That's the only element that are in common with both A and B. And A and B are called disjoint if A intersect B is empty, i.e. they have no elements in common. Now if we have think of this as a large set here, it's some universe U, maybe U is the rational numbers. We can draw this in pictures. Say we have a subset A of the rational numbers and a subset B of the rational numbers. This is A and B. Then A union B is going to be this filled in set here. Okay. Now if we had, let's say, two other subsets of U, C and D, so this was A, this was B, this was A union B. Let's say we had C and D, and we're interested in the intersection of C and D. That's just going to be this shaded region right here. This is where the two sets C and D intersect. Okay, so looking ahead just a little bit, and so you're aware of it, let's say we'd like to know how large, let's assume that A and B are finite. How large is the size of the set A union B? Well, you add up all the elements in A, you add up all the elements in B, and you have to subtract their intersection. This is called the inclusion-exclusion formula. It makes sense though. So, here we have A, it's 3 elements, and B is 3 elements, but A union B is only 5 elements because we only count this element 1 here once. We don't want to count it twice. So A union B is the size of A plus the size of B. 3 plus 3 is 6, minus the size of their intersection, which is 1 here. So 5 equals 3 plus 3 minus 1. I should also mention the subtraction set difference operator. So that's written A minus B. And this is equal to the set of all elements x such that x is in A and x is not in B. Okay, so if we drew a picture for this, and here was A and here was B, then A subtracted out B, or A minus B, is this shaded region right here. It's A, and then I've cut out this subset B of A. Another example would be, let's say I have A, and then I have B here. So this is B, this set is A. Again, A minus B would still be this shaded region here. Okay, and we can talk about some other properties of these operations on sets. For example, we have a distributive law. A intersect B union C is equal to the set A intersect B union A intersect C. It's just like when we did the distributive law for Boolean formulas. So we also have A union B intersect C is equal to A union B intersect A union C. And let's say that let's fix a universe U, and let's say that we have A is a subset of U, and we can look at something called the complement of A. Sorry, complement of A. It's written A bar, and A bar is equal to the set of all x such that x is in U and x is not in A. So in pictures, if I were to draw a picture for this, if this was U, and here we have A, the set A, then A complement is going to be everything outside of A. Okay. Now, if you haven't specified your universe U, it doesn't make sense to write A complement. For example, if you tell me that A equals 1, 2, 3, and you don't tell me what the universe U is, and then you say A complement, well, I don't know what A complement is. I mean, unless you've given me more information. I mean, A is 1, 2, 3. What's the universe? Is the universe all positive? Is it all integers, or is the universe just the numbers 1, 2, 3, 4? You know, so if U is 1, 2, 3, 4, then A complement is just 4, because it's everything in U that's not in A. But if the universe were 1, 2, 3, 4, 5, then A complement would be 4, 5. So you have to specify your universe before you really talk about the complement of a set. Now, if you just want to talk about set difference or intersections or unions, you don't need to specify a universe beforehand. So we also have De Morgan's laws for sets. So again, let's assume that we've specified some universe U, and I want to look at A intersect B complement. This turns out to be equal to the complement of A union the complement of B. And also, the complement of A union B is, not surprisingly, the complement of A intersect the complement of B. So these are De Morgan's laws. And let me just show you that we already know how to prove these identities. You may not realize it, but we really do. So let's prove this identity number 1 here. How do we prove this? Well, what is the definition of A intersect B complement? It's the set of all x such that x is not in A intersect B. Okay, so it's the set of all x such that x is not in A intersect B. Okay, well, this is equal to the set of all x such that it's not the case that x is an element of A intersect B. right? Good. So this is the set of all x such that it's not the case that x is in A and x is in B. This is equal to the set of all x. Now we're using De Morgan's laws as we have learned them in the past in the course. So we have a negation here and we have an and. So it's not the case that x is in A, or it's not the case that x is in B. This is equal to the set of all x such that x is not in A, or x is not in B. And this is equal to the set of all x such that x is in A complement, or x is in B complement. But this definition, this is the set of all x such that x is in A complement or x is in B complement. Well, I guess we could write one more step. This is the set of all x such that x is in A complement union B complement. And this is just A complement union B complement. So I guess the point of this is just to say that the De Morgan's laws for sets follow. Where did we use De Morgan's law? For formulas, we used it right here to go from this step to this step. We used De Morgan's for formulas, namely that you have a negation of x in A and x in B. That's negation x in A or negation x in B. And then we push that forward through and we see that x is in not A or not B, and so x is in A complement or B complement. So we prove that the negation or the complement of A intersect B is the complement of A union the complement of B.